Hey, what's up, YouTube? Today I want to talk about some vertical curve problems and basically go over what I think is the most important part about learning rise over run and grade percentages. Okay, so the first thing we're going to note is that the rise is basically the delta y, or change in elevation, and then the run is basically the horizontal control, or the x direction. So what you're going to find in most cases is that the grade is basically defined by rise over run, or the units are feet over feet, and then we multiply by 100 to get a percentage. So when you say a grade of 5%, that basically means a rise of 5 feet, or it could be a drop over a run, or a horizontal distance of 100 feet. And so next we get feet over stations, and this is basically because a lot of roads are meant for cars to be traveled on, and they're listed every 100 feet because that makes it easier for us to track the horizontal distance. And basically, trucks can't really go over steep grades, so it makes more sense to list the horizontal constraint in terms of station. So what does that mean for the grade percentage? Well, our typical units end up being feet for the rise and stations for the run. And this makes sense because if you have a grade of 5%, a car or truck can easily travel up that. And that means for every 100 horizontal feet, that means it goes up 5 feet. And basically, we can check the units because feet over stations, and if we convert stations back into feet, we multiply by 100 feet over one station. And that's basically the same as saying feet over feet times 100, and that is basically a percentage. So if we see the units feet over station, that means it's automatically in a percentage already. So let's look at a grade example problem, and we have 4 points, A, B, C, and D, and it looks like we have an elevation of 90, 80, and 70. So take 2.7 minutes to see if you can solve this problem, and let's get back. Okay, here are the answers for segment AB. We get a rise of 11 feet over one station. That's 11% grade. For segment BC, we get a drop of -6 feet, and that's over a horizontal distance of 1.2 stations. That gives us a -5% grade. And then for CD, we're going upwards, a rise of 15 feet and a run of 0.8 stations. And basically, that's 80 feet, and so that's 18.75% grade. Just for clarification, if segment CD was in feet, we would get 15 feet over 80 feet times 100 is the same as 18.75% grade. So those are easy examples, and just to get used to kind of working with feet and stations, and it just makes for easy math because you basically just take the elevation difference and then divide it by the number of stations, and then you get your grade percentage. So that saves us actually a lot of time on the exam because we don't have to deal with multiplying by 100 each time and converting hundredth place decimals. Okay, so if you look at this diagram, it's a great example of how slopes and grades kind of go into our city planning and city streets. And basically, the whole idea is that these streets are designed for water runoff to escape the sidewalk and go into the catch basin. So that's basically number one is showing the sidewalk, and number two is showing the catch basin. And as you can see, that red arrow there is the cross slope, and typically designers design this to be a minimum of 2%, and so the water just starts from 1 and ends up at 2. And then you can see that between 2 and 2A is kind of like the gutter of the street, and basically it's flowing downhill from 2 to 2A, and so any kind of runoff from the sidewalk in between 2 and 2A is going into this gutter, and then it's going into the catch basin. So let's just say the water goes into number 2, the catch basin. Well, at the bottom of that catch basin at number 3, there is a deeper part of that, and that's basically to capture all the solids. And so what happens when it rains is that all those solids go down at the bottom of the catch basin, number 3, but eventually that liquids flow up, rises up, and it flows down from 3 to 4. And so keep in mind that we are maintaining this 2% downward slope because the water needs to drain out. And so from number 3 to number 4, we actually call that a culvert. And so the culvert connects to the manhole, and the water drops down. And so now what we're looking at is we're inside the bottom of the manhole, and actually when it gets to the manhole, it actually just converts where you see that arrow. That is the invert elevation, and it goes down into the main. And so actually at the bottom of this manhole is just, it's a concrete base. And so basically the culvert just leads into the invert elevation, and it flows down the main at number 4. And it flows down this main until it gets to a treatment facility center where they will treat the stormwater runoff or the sewer and decontaminate it. The interesting thing to know about this diagram is that if we look at kind of the length between 2 and 2A, we're showing that it's a downward slope. And so if we're to say that the minimum slope between 2 and 2A is 2%, that means that if we're given any horizontal distance, we can figure out the vertical distance. Or we say it's a 2% slope and we're given a vertical distance, then we can basically figure out what the horizontal distance is because we know the grade. And so if we look at number 4, where the culvert enters the manhole, basically there's usually a minimum slope, but it actually won't match the slope above on the top of the manholes. And this is because basically the street is going to follow the existing elevations, but the manhole or the sewer main will actually maintain a different type of slope and at least a 2% minimum so that the stormwater drains off. And this kind of leads to manholes having different heights, and basically because it's changing at a different rate than the street above it. So this creates for some interesting kind of elevation differences for manholes. By the way, if you guys don't want your grades or your test scores to end up in the gutter, make sure to smash that like button. Water can pond and create hazards. Minimum grades define the amount of rise/run a sewer pipe or sidewalk can have. The minimum slope percentage for sidewalk or sanitary gravity sewers is typically 2%. However, in practice, sanitary sewers and streets can be designed for higher slopes to account for surface runoff and storm events. Okay, let's talk about some vertical curves here. So we have this diagram, and basically it shows the station markers. And what we can see is that there's station 1, station 2, and then station 3 for this vertical curve. And what's going on is that the stations are defining where we are along the curve. So just kind of imagine a car driving around the curve. The distance that the car is traveling is basically the stations. And so we can figure out what the turning point is, and that's basically defined by negative G1 over R. And X is in stations, G is in percent. Usually they're going to give you some sort of grade, 2, 3, 4%. And then R is basically percent per station. Okay, so L over 2 is equal to basically X plus A defined by the location of the turning point. And we can also define the turning point in terms of G1, and that's just negative G1 over R. G is in percent, R is in percent per stations. And basically, R can be defined as G1 minus, or sorry, G2 minus G1 over L, which is basically the arc length in stations. So if we look at the general equation for the elevation at any point along the curve as a function of x, we see that it takes the form of a quadratic equation. Basically rx squared over 2 plus g1 times x plus the elevation of the BBC. This should be an easy equation to solve provided that you have the right distance. So get used to putting x in terms of stations, because if we look at the first term, rx squared over 2, we know that we can find r. Basically that's g2 minus g1 over L. They have to give you g2, they have to give you g1. And so what we get for the units of r is basically percent over station times x squared, which is basically stations squared. So in the first term, we're going to get the result output of stations. And this is consistent throughout the whole equation. One interesting thing to note about R is that it is also the units of feet over station squared. So plugging in x with stations will cancel out the stations and leave you with feet, which is the desired unit for an elevation. While we're on the topic of stations, let's talk about the stationing of the PI. Basically, the PI is in the center of the BVC, beginning of the vertical curve, and the EVC, the end of the vertical curve. And this is by design. So we know that the distance between the two is L over 2, and basically L is just the arc length. And so half of that is basically the midpoint, and that's where the PI is always located, by definition. Also, we can write the stationing for the EVC in terms of the BVC by adding the entire arc length. So in summary, if we know the stationing of the PI and we know the arc length, we can find either the stationing for the BVC or the EVC. And that is how the problems are typically solved for the stationing. Okay, so we'll notice there's two types of curves, a vertical sag curve and a vertical crest curve. And basically the vertical sag curve, we got the PI at the bottom. Vertical crest curve, we got the PI at the top. Basically one's a hill, one's a valley. And so these equations that we get are basically just saying that the elevation of the BVC can be related to the elevation of the PI. And that's related to negative G1 because it is actually going downwards, and we multiply it by L over 2. As we said before, the PI is always located L over 2, halfway between the BVC and the EVC. Same thing with the next equation. The elevation of the EVC is equal to the elevation of the PI plus G2 over L over 2. And these equations both work out given with the signs, because basically the elevation of the BVC is higher in the sag curve, and the elevation of the BVC is lower in the vertical crest curve. So those signs will work each other out. And basically, when we go to look at G1, because G1 says elevation of the PI minus elevation of the BC is L over 2, and that'll give us the correct sign for both G1 and G2. Same thing, we have G2, the elevation of the EVC minus the elevation of PI. In the first example, the elevation of the EVC is greater than the elevation of the PI. We'll get a positive G2. And then for the next one, the elevation of the PI is higher than the elevation of the EVC, so we'll get a negative G2. And that is consistent with what we expect for both the vertical sag curve and the vertical crest curve. By the way, all these equations are made available at the website. Visit passcivilpe.com. Link in the description below. Okay, thanks. Bye. Who doesn't like free content? Please like and subscribe. Tell me how I could do better. Leave a comment wishing which topics you would like to be covered next. I hope you have a great day. Thank you for watching. Pass Civil PE.